it's all about the cookie, and it's all about the dum dum da 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 crumb. All right. So let's start with most common pin code, and since you have already been this here as audience, you might already know this. This was a test performed by a Norwegian guy. He met a class of high school students and asked them to choose a pin number that they would definitely, without a doubt, remember 1 month from now. And then he did some statistics and figured out that the most common pin was
0007.
oh no, not the most one. No.
1337.
Sorry.
1337.
You're too. Okay, so there was a difference actually between boys and girls. Among girls, it was 1, 2, 3, 4, and among boys. Yeah. So, oh yeah, of course. Yeah, mine as well. And what's the relation? Everyone should know. Sorry.
That's going to be in a specific group of people.
Yeah.
Not all our gamers.
No, absolutely. Yeah, specific group of people, definitely. But yeah, of course. And the relation is, of course, that this is cool. Hacking is cool. So is yeah. Stealing passwords is cool. So we've seen a number of these, right? 145 million, 8 million, I don't know how many million, all leaked in password databases, and then you have password hash cracking, and all of a sudden you have 1.2 billion records stolen. And this was not very long ago that this was proclaimed that Russian hackers had stolen 1.2 billion records. And you get these wonderful websites. Puntlist actually collects all these, and you get 366 million account credentials, and a number of leaks, and a number of passwords, email addresses. Very nice. And if you want another password, another credentials, then why don't you sign up today? And then you can have another one. So so that's the situation, and that's how it looks. And the interesting thing that is to me is that all these passwords are still on the internet. You still manage to send them around, and that's what we're going to talk about. So I'm a founder and CEO of Assured Security, a very newly founded company, and something that you will hear more about, not today, but in the recent future, I hope. I have a PhD in application security. I wrote a thesis called Securing the Mashed Up Web. I've been here, talked about some topics that I brought up there as well. Integration of third-party code without leaking information, for example. I'm currently a postdoc researcher at the University of Saarbrücken and Saarland University, and at Chalmers part-time. I look into some topics like privacy-preserving biometric authentication, how you can scan a fingerprint without and verify it without leaking details of the fingerprint of the person being fingerprinted, and still have a go on the result. I look a little bit at the content security policy and how that interacts with browser extensions, and to be fair, it doesn't. And decentralized client-side single sign-on, and that's exactly the topic for today. How can we decentralize and do client-side verification of passwords and put that together in a single sign-on service. And I happen to be an OWASP Gothenburg chapter leader, co-leader, to be fair. Yeah, so let's see. Traditionally, right, you have your browser, you type in your password, more advanced password than that, please. And you submit your password to a server, and hopefully, not always, but hopefully you do it over HTTPS. So at least in transit, it's protected. But what we can note here is that, it's being stored in a database, but so far in this setup, the password is actually in plain text in 3 different places. Hopefully, though, you hashed the password before storing it in the database. So you have some kind of security, at least when storing the passwords. But we still see, right, hashed password databases being stolen, leaked, and then the passwords cracked. So even though this is not optimal, at least you have some kind of security there. But it still remains. We have it in clear text in the browser. If something, say cross-site scripting, whatever, enters your browser and you enter your password, it's leaked immediately. And same on the server side. Even if it's protected in transit, it arrives in plain text, then it's hashed by the web application and compared to the database. But before that, it's in plain text. If you consider something interrupting between the actual web server and the actual web application, or managing to somehow manipulate the web application itself, the password is right there in plain text. So that's what we want to move away from. And one way of doing it so far, and the benefit here is that you get a cookie, and yeah, and the server says, here, take a cookie. So the next step would be to have an authentication service, and we've seen these a number of times. You have Facebook, for example, and Twitter, and Google, and so on, where the browser asks the server to log in. Is it okay if I log in? Yes, it's okay if you have the right credentials for Facebook. Facebook has this login service or authentication service. I get my credentials checked with Facebook, and I present a token to the server that this is actually correct. So I share the secret password with Facebook, but Facebook alone. I don't need to send it out to every server that I visit. This is progress. And this is also single sign-on. You enter it once, and it's just happening in the background. You don't need to think so much about it. So Facebook presents you with a token. You send that. Yes, Facebook definitely trusts me. Okay, here, take a cookie. But it remains still that in the browser and on Facebook, it arrives on Facebook in plain text. If, and this is a big if, Facebook were to be hacked, then they could intercept a number of passwords, or they could leak the database. But it's Facebook, so we haven't really found. I mean, it doesn't happen very often. At least that these major sites get hacked. No, it's unheard of. Yeah. So this is more targeted towards the audience that I had in Stockholm, but we talked a little bit about broken authentication and session management, and how an attacker can influence sessions, and one such implementation mistake that I found recently and during a pen test was clippers.is. The pen test report is actually available online at Cure53's website, and they use a protocol called SRP, and there's a parameter in that protocol that is not allowed to be 0 modulus n. And of course, this was just mentioned in the protocol as a parenthesis in the end. It was assumed that this was common knowledge, which made me think that, I wonder if they noticed that particular detail. And they didn't, of course. So if A is 0, then the result of the calculation is 0, and then you can authenticate with the hash of 0. Congratulations. Lovely, actually. Anyway, cross-site scripting, this you know. It's 15 years and still going strong. And from a research perspective, I mean, there is not much more research going on in the cross-site scripting area because it's considered solved. The major conferences generally do not accept new papers on cross-site scripting because there's not much more to say. But it still remains the most prominent vulnerability online. And it's because it's so damn simple to make a single mistake and you're screwed. And as we said earlier, that if you have a cross-site scripting issue in your browser, then you will have a problem, for example, with authentication, where an attacker can either steal information when you enter it in the browser, or it can present its own login form, say that, oh, sorry, you've been logged out, enter your password. So, and so in the end, why do you need to share your password? I really don't see the reason, and that's something that I thought I'd look into more. And this comes from a number of pen tests, actually, that I did recently. Clippers I mentioned, SRP, secure remote password. Here you share an identifier with the server, not the password and not something that can be reversed or tracked back to the actual password, but just an identifier. And if I can calculate and give you a value that you can calculate and arrive at the same shared secret, then you can consider me as verified or logged in. Another company, they had another idea. They encrypt the user profile as a blob. They can't actually even see what your user profile is, but it sends the blob to you. If you can decrypt it, then there are further other keys inside the blob that can actually be used to verify your identity. But they don't know the secret, and it's only you, if you know the password, who are able to decrypt the blob. And then not really client-side password verification, but a quite neat idea. And this is Minilock, and Minilock is a file encryption service, but made very simple. You simply enter your password, and on the fly, they generate the encryption keys, decryption keys, such that when you get a very small identifier, which actually represents your public key, which you can share with your peers. And it's generated every time. So you don't need to store your actual secret key anywhere. You don't need to have you don't have to have it written down on a large piece of paper or stored in a computer somewhere. It's generated, and that's it. Typically, generating keys in RSA, for example, takes time, and so it's time consuming. It's not in this case because it builds on a very small electronic what's called ECC. Yeah. Anyway, elliptic cars. Thank you. Yes, and the keys are very small. So, without going into the details of Mendelog, I was wondering if this could actually be used instead for authentication. You see here, the keys are generated, never stored, can't be deleted, but you can forget them. If you forget your password, then you also forget your keys, and then you also forget your identity. That's kind of bad. But the way they implement it is very hard to brute force as well. They use scrypt among other things, which means that brute forcing would take either a huge amount of memory or a huge amount of time. The negative side of this is that if you forget your password, you're screwed. But let's think about this for a second about like in an authentication setting instead. And I was imagining a challenge response type of scheme where I'd like to log in. Okay, so are you able to sign this string, this very random string? Then of course, if you can sign it, then I know you have the correct keys that was derived from your password. And you could sign the key, the string, so and I could verify with your public ID or identifier, which, yeah, the public key, which means that I can actually trust that you knew the password when I gave you this challenge. So I enter the password and sign and provide the signature as the proof. Simple enough. Here, take a cookie. So this is the part that I was looking into and wanted to understand more. What can we actually do here? The idea is simple, but how would we implement it? And can we make it even better? So what we would like to see is client-side password verification. Okay, we have some kind of idea about that. We don't want the password to leave the browser anymore. We want to instead receive challenges and send responses. Yeah, that's the way to go. But this is very annoying if you, again, have to go back to the situation where you have one password for each site. And so we would like this kind of Facebook-like authentication service. You have one service, you enter your password once, and you get access to all your sites. We would like also to have password resets. As many would definitely concur with, I'm very forgetful. I definitely need this. I'm sure I'm not really the only one, but something I definitely wanted to look into. Can we implement password reset when we derive our public and private key directly from the password? That was a challenge, but interesting one. And I wanted to implement single sign-on, and this is because I'm lazy also. I'm not just forgetful, I'm lazy. I want to log in once, and then whenever I get to a new web page I want to log in to, then I don't want to have to generate the keys again. It takes time. I'm lazy. I want to just be able to click login and it's done. Right. So let's start with client-side password verification. Again, don't send the password around. We want to verify it locally. And we want it to be decentralized in that sense. So if we don't have a single point of failure, there's no password database that you can leak or crack, or and you can't intercept the password anywhere. So decentralized verification. And how do we store the credentials? Well, if we have this generating the keys directly on the fly, then we actually really don't need or want to store the credentials anywhere. Why should we? And the idea then to how to verify is generate the keys on the fly, sign the challenge, and respond with a public key and signature. And the server uses the public key to map to my actual username and verifies me using the signature that I'm actually this person. I'm going to give you I'm not going to go into the details, but I am going to show you at least the academic look of the password protocol. And without going into detail, yes, a randomly chosen secret challenge, entering the password, hashing, generating keys, sending back the signature, a timestamp when the signature was signed, and the public key. I realize I made a nice mistake here. Do you notice?
Where's the C?
PK? We don't want to send P there. Either way, not going to bother you. And decentralized authentication service. So at the moment it looks like this, even though we have major websites that we can use for authentication services. They all have their own centralized database. So we would like to have our own database with our own, well, passwords, or rather just not really passwords, but our own means of verifying ourselves. And we would like to have that for every person. So you have your own set of credentials, your own database-ish, and I have my own, and we don't need to share anything. We don't need to consider or overlap or interchange or anything. And how could we do that? Well, so we would like that to actually, in order for it to have decentralization, we would like everything to be run on the client. And the optimal solution would be to run it as a browser extension. But then any website that you want to authenticate with would have to know that I have this browser extension installed. Most user would not have, some user would have. So the second best option is to have it as a web page that only delivers the code, nothing else. And then everything is executed on the client side. That's what I have implemented. I plan to implement the browser extension as well. It's a very simple procedure from this website page, but at the moment that's I use the backup plan. And to this service, the server sends the challenge and its own identification. For example, the URL of the web page that I'm visiting. And I return the signed URL, all the parts necessary for it to verify that I signed into this particular page, for me to authorize this page to verify me. And and so on. I'm not going to go into any detail and about how that is implemented, because simply it's just a small change in the protocol. We've already been through that. Rather, I'd like to talk about password reset. And this was a tough nut. And it took some time. And I have a really clever office mate. And we sat down, we have talked a lot about cryptography. He works on cryptographic protocols, and we did this biometric protocol together. After discussing back and forth for a while how we could maybe add something, remove something, I got the idea that, well, so this procedure, if you remember, we took the user credentials, we hashed them, then we generated the keys. But there's an intermediate step there. We have an opportunity here to actually modify the hash. If we have an existing, the hash of the current password and another value, eta value it's called here, and then we could actually XOR those two, and if the hash changes, then we can modify the eta value in the same way, such that the result of the two still matches the input to the key generation algorithm. So we have a hash h, we have a new hash h prime, and given we have the eta value, we want the input to the key generator to be alpha. Then we can calculate a new eta prime by XORing h and eta and h prime. And now eta prime h prime is the same as eta h, and it's equal to alpha. A bit technical. I'd love to get feedback on this. It's something that I have thought about. It's something that other people have thought about, but it's not given that this is actually secure. And a lot of people, including myself, question how can this simple solution actually hold in the long run. And the idea is that since eta is completely random to begin with, any XOR, however, with the eta value will also be random. And the only thing that leaks actually is the binary complement between h and h prime. And that is, for a cryptographically secure hash, that should not have any influence whatsoever on actually being able to crack the password. But any input is very much appreciated. The updated protocol is this part. The alpha is now the input to the key generation. So, single sign-on. We have solved all the other obstacles, hopefully. Well, with my best guess, it's solved. And but we only want to enter the password once. And since, well, what we could do is store the secret key. Then we could create this, then we could respond at any time using the secret key. We just generate a new signature every time, no problem. But the idea here is to generate the secret key on the fly, not have to store it, and not compromise, well, prevent potential compromise of the secret key by storing it. That's the whole idea and purpose. So how to deal with this, and the idea is now to create temporary keys, and these session keys are signed with the master key. So using the public ID, the public official key, you can verify that these session keys are valid for this lifetime. And you use a timestamp to verify that. If the current timestamp, the time when these session keys were generated, exceeds a certain value, then it's not valid anymore, and you refuse to, then you abort simply. So again, I'm only going to briefly show you this. It's mainly to scare you off in actually understanding this. Bow! Okay. Demo time? No, we take that later. I need to do some setup before that. And apart from that, so the idea, we have looked at the browser side, we have looked at what code runs there, we have looked at protocol. What's important to notice still is that if you have an injection on the browser side, still you can compromise the password. So the idea with this single sign-on service is that this is the actually single point of failure, but it's distributed, so you can only attack one user at a time. It's also, at the moment, as I have designed it, extremely brief on code. So the code base is minimal. I'm trying to actually get rid of some other libraries and just use, there's no jQuery. jQuery is way too advanced for these purposes. You should not be able to attack my code. That's my target. I'm happy also to have feedback on that when the code is actually released, to see if someone can crack it. I'd love that. The other part is if the protocol is actually not secure. And that's also something I stake my name in. I can't guarantee that it's 100% secure because I was the one who invented it, so I'm pretty much blind to its faults and failures. So again, it could be very much so that this is a broken protocol just as soon as it's released, and I'd like feedback on that. So in the end, we managed to do this. We get a challenge, we respond, the server says, here, take a cookie. And that's exactly that. Passwords get you the cookies, and cookies gets you the session. But you have to make sure that your cookies are your cookies and not stolen by somebody else. And now I hope to be able to show you a small, tiny video clip. This is something you always should prepare for.
That was a bit low.
Yeah. Here, take a cookie. By the time you're done, I think you will feel righteous. Yeah. So, thank you. I hope you enjoyed it.